Hello, everyone, and welcome to this session on Big Data with Cloud Computing. You have likely heard the terms big data and cloud computing before. If you are involved with cloud application development, you may even have experience with them. These two go hand in hand with many public cloud services performing big data analytics. With software as a service becoming increasingly popular, keeping up to date with cloud infrastructure best practices and the types of data that can be stored in large quantities is very crucial. Both big data and cloud computing play a huge role in this digital society. The two linked together allow people with great ideas but limited resources a chance at business success. In this session, you will learn all about big data with cloud computing. So, without further ado, let's start with the session. But before we begin the session, make sure to subscribe to our channel and press the bell icon so that you'll never miss any update from us.
Introduction of big data. So say for example, this is a Tesla Model 3 car. It has all these functionality. It is a like electric vehicle. It has all the model where like wide side mirror, power trunk, LED ambient light, BSD system, head-up display, and all. Like these are the features, but all these features are enabled with the help of sensors. And if you see how much data it creates, so this particular smart car create 20 terabyte of data per day. Just one car create 20 terabyte of data. So you can imagine how much data just one car is create. Or if on usual, like just usually, if at one particular place, if they have like kind of 1 million this car, how much data can be created per day? Similarly, if you see this Uber, everyone nowadays uses Uber. If you want to travel, this particular Uber application, you can just specify your source and destination. It can easily kind of first it searches your location on the map. What is the destination location? Then it tries to find or explore the data from different cars. So each of the car has an enabled sensor which kind of specifies their current location. Then there is an algorithm for Uber which kind of compares your current location or the source location along with the different location of the car, and then try to combine which car is in the nearest location of your destination and which driver is able to or want to give a ride to you. And then that particular car can come to your place and you can go. Not only that, during your travel you can kind of navigate directly that okay, where are you at any time, which direction your car is going to take, and everything. After you reach your destination, you can get your payment slip online. You don't even have to do anything. If you are paying by cash, your receipt, or if you're paying by card, your receipt will automatically generated and mailed to you as well as uploaded on your app. So all these operations are performed with data, your source and destination, then the location of the car in terms of XYZ axis, then which path. Again, taking the path also uses a lot of data, like how many paths are available from your source to destination, which path is the will take the lowest time, which path has more traffic. It always try to kind of reduce the traffic, or it overall kind of optimizes your overall travel time. Considering about other application like Google Home or Alexa, you just have to connect all your devices with Google Home or Alexa, and it is automatically trained. So when you speak that okay, uh, Google just open play this song, and your iPad or your system is already connected and start playing that song. Alexa, just switch on the light. Or if your light is kind of smart light with the multiple features, you can say that okay, Alexa, just open the light with yellow color. Even if it's yellow color, you can just say that okay, Alexa, just change the light color of light from yellow to blue. So it kind of uses your voice data, which is in different format, try to convert that data into machine understandable language, matches that with their available database, and then based on whatever result it receive, it kind of try to perform the operation whichever is desired. If it doesn't understand, or if you're not speaking like in the right way, it will say that okay, sorry, I don't understand, can you please repeat, or this information is not available, do you want me to do anything else, something like that. So all this operation uses a lot of data, and it requires different kind of data processing, which is not very generic to what was done in the past. Similarly, we have another example of this smart shoes, which is mostly weared by some runners or athletes. It kind of provide not only comfort but also captures the activity of that particular person, how fast it's running. If there is any issue with their ankle or feet, it automatically sends a message to the user on their mobile phone saying that you are walking in this way. You are putting a lot of pressure on your front feet. You have to walk slowly or something like that. Sometimes it also gives like creates some vibration to reduce the stress of the feet, which is very helpful for the runner. So again, creating this running data, or how much speed the person is walking, it can combine some data with what street it is following. It also uses some of the body activity, like what is the body temperature at that particular period of time, whether the person is sweating more or not. In terms of it is programmed. So combining all these data will create a sort of helpful function for the user and the person who is using this particular application. Similarly, we have this smart watch or a smart ring, which kind of not only gives you the time but also tells you what is your heart rate, or what is your body temperature, how fast you are moving. Current smartwatch, you can also receive calls or get some notification based on your activity, what you are performing. So it shows that data is everywhere. Now, all these applications create a lot of data. The question comes is, what do we do with these data? We have to have some mechanism or some technique so that we can kind of generate some important function. As I already gave the example of Uber, if this application is not available, if we already have like say for example, if you have your location, if you have the car's location, you have your destination location, you have the path information. Now you need to order the application, that it need to be some application that kind of combines all this information and then provide you the actual path. Okay, you can use this particular actual path, provide you the car, and the car will again take that particular actual path and take you to the destination. So how this how all these big data is utilized to perform these application is very important to understand. So it says that increasing the number of, like the number of machines are increasing, and each device collects the data. So it research shows that all these machines plus some social media are the biggest source of the data, or we can say big data. Now, consider 1 minute of last year. So if you see just 1 minute, you can see this picture shows how much data got created. So in just 1 minute, there are 5.7 million search performed on Google. There are 6 million online people performing shopping. There are 856 hours of webinar is happening on Zoom. The 100,000 users are connecting on Teams. 452,000 users are streaming on Netflix in just 1 minute, and $283,000 are spent on Amazon, like by customers. So you can see just in 1 minute, all these operations are performing, and each of these operations create data, and each of the event like interaction will create a huge amount of data. So the question comes is, why this big data is useful? It is useful for performing some operation. See, for example, I will give you another example of this Boeing 787 aircraft. This Boeing 787 aircraft is fully automatic, and although there are pilots who can control the plane, but it can easily be controlled, or it can easily be driven in an autopilot mode without help of any human intervention. So there are a lot of sensors embedded in the whole plane in terms of smart radar that kind of captures the information about what is the altitude and latitude of that particular plane. So that and that using that particular information, it can instruct the engine to increase or reduce the speed of the plane, or go upward or go downward. It has again bulkhead that kind of try to move the plane from either left or right, or which direction or which particular coordinate. It has the pressure control that kind of increases. So if there is any low pressure happen in the plane, it can automatically drops the oxygen mask, so that any of the person present in the plane doesn't got affected too much. It also has a temperature controller that kind of controls the temperature of the plane regardless of the height of plane where it is flying. And there are so many other features embedded in the plane. So the plane, it uses the previous information. It captures the current information in terms of the dynamics, in terms of the coordinates, in terms of the weight of the whole overall weight of the passengers and all. uh, what is the location, what is the pressure, what is the cloud density, how much wind pressure is there, to control the movement of the plane in terms of what is the engine speed, what should be the engine speed, how much, or what is the upthrust taken by the plane, what temperature can be controlled, how much temperature can be controlled, pressure can be controlled, and like takeoff and landing speed to consider. So this is one of the best example of the big data. So next come is, what is the definition of big data? So Wikipedia defines big data as all encompassing term for any collection of data set so large and complex that it becomes difficult to process using on-hand data management tool or traditional data processing application. So picture collected from camera can be a part of data if you have any application which kind of has like thousands of camera creating or capturing the picture, and now you kind of use all those picture in some way. The best example is in terms of like smart camera which is set up on the street of any city. Actually those cameras are combined, so the pictures or images or videos captured from all those cameras can be combined to see that, okay, if the person, a bad person, or a thief who is which way he is going or which way he is moving. So in big data we are not like considering very small kind of data. We need to consider such a amount of data which is very hard or which is very complex to process or store or manage by any traditional data processing application. We can't say that it cannot be processed. It can be processed, but the processing can is so difficult and it consumes so much time that it's better not to process. So say for example, if you have one laptop and you want to kind of detect a thief and you have say for example 500 cameras already installed, each one is capturing sending you a video. Now video is, even if it is a CCTV camera, the video size is huge. Now if you have 100 camera, you have to kind of combine all the 100 camera video feed. Then you have to match each of the, like you have to convert the video feed into kind of image way so that you can compare the images with the image of that particular thief or associated person. Now if you have just one computer, it becomes like very hard, or even if you are able to process, it will take kind of days and days to process or to find that particular person in the video feed of, say for example, 1 hour. If it takes like few days to process, then it becomes kind of infeasible or not useful to even use or even think about using one computer to process, because in like say for example 10 day, that particular person may be gone somewhere else. So that's why we see that it's difficult, although it can be possible, but it is very difficult to process using some basic data management tool like Excel or some simple computer or some simple application. Next question comes is, how big is the big data? So previously, like in 2008, Google processes 20 petabyte of data. Now can someone tell me what is the petabyte? So we already know that we have byte, then we have kilobyte, then megabyte, then gigabyte. Now we are talking about petabyte. Okay, okay, it's 1024 terabyte. So you can imagine that 1024 terabyte, considering terabyte is so big now. Nowadays it is we consider like now if you see some of the laptops or some of the machines, they have 2 TB or 5 TB of storage. We have some external hard disk of 10 TB or even 20 TB, but like in 2008 Google processes 20 petabyte of data, and this is 2022. So in 2009 it increases, like Facebook has 2.5 petabyte of data and it processes 15 terabyte every day. But if you see the current time, we don't process in petabyte like Google and like now Meta, which is advanced name of Facebook. They process is not in petabyte, they process is in exabyte. Like Facebook uses 2.5, Facebook processes 2.5 exabyte of data per day. Not only exabyte, now we are considering, or we are in a time where we have to consider yottabyte and zettabyte of data, which you can imagine how big is this value. Considering petabyte is big, but now when we process this yottabyte or zettabyte of data, that is more and more complex. I think you guys must have heard about last year. So we got some of the images of a black hole. uh, so how does the black hole looks like? So to process or to get that particular image, they are processing just one simple application. They are processing 20 or more than 20 petabyte of data. So they are carrying hard disk in their hand, and then they have like big supercomputers to process all those images collected from different like different dimensions to get just one image. So you can imagine just one application is uses more than 20 petabyte of data. So if you are considering multiple such kind of application, how much data it will require? So now the question come is, although we have data, now what do we want to you do with the data? So the basic thing is like we can specify that as a data integration process. So our aim is to integrate different data to discover something new, to make it easily accessible, to monitor some of the operations, and finally using this discovery, accessing and monitoring, we want to model such as smart city, and we want to transform. So what do we want to transform? We want to transform the human life in terms of how humans are working, such as consider an example as a healthcare. So in smart healthcare, all the users are enabled with some smart watch and some smart ring with smart waistband, and also that uh, all the people, all the associated people, they already specified their like medical history, and with these smart devices, their activities already like always monitoring in terms of their heart rate, how much is their blood glucose level, how much is their blood pressure, and each time all these data are combining, and if there is any like even a probability of happening of like heart attack, or if there is a probability of increasing the blood glucose level, the application can automatically tells user that okay, now your blood glucose level is going to increase, don't eat or go for running or take an insulin injection or something like that. Or if it's a bit serious, then it will automatically say that okay, now it's this is serious condition, it automatically calls the ambulance, so that ambulance can come and take the patient to the hospital, so that that particular patient can get some immediate medical attention. So all these are kind of transforming the way how things work in terms of healthcare, in terms of agriculture, in terms of how people are driving or traveling from one location to other location, and some in terms of uh, music, how you're listening your music, how you are interacting, you don't have to switch on the light, you can just ask Alexa or Google Home to switch on or switch off the light. Sometimes you don't even have to ask. So there are some current application where that particular device will kind of detect that okay, now you are leaving from office, and you, since your direction is going towards the home, so it automatically kind of warms or like switch on the AC, so that when before you reach home, your house will be kind of in the suitable temperature that you designed to or you specified your house to be at. So all these things kind of transform the how human being, or how we are living and how we are interacting with each other or with the environment. Next is data integration. So in our last lecture, I already discussed that data comes in all shape and size. We can have structured data, or we can have unstructured data. We can have like just some simple flat file where we have all the table format. We have some relational data in terms of not only just flat file, we can have in some pictorial way. We can have some XML and JSON file. So all these data need to be kind of handled in some way. uh, so why do we need data integration process? So question come is there any requirement? Why do we need data integration? So the first thing is we want to reduce the complexity. Say for example, if again I repeat my previous example, which is Uber app example, we have an application where we have kind of 10,000 user at a time in one city is kind of looking for a ride from their source to destination. So they have their XYZ access location, which is not very like comfortable. Then we have 10,000 again for 10,000 for each user. Say for example, we have at least we have one car, so we have 10,000 cars also available in the city, uh, and the car has the car location. The car has the driver willing to travel or not travel. So car has their own location information, the driver's information. Uh, what is the it also uses the traffic location, whether the traffic is smooth or it's a heavy traffic, which street has a heavy traffic. uh, Now all these data independently is very complicated, and it's not easy to understand. So the first aim of data is to kind of reduce the complexity and make it easily understandable by the application. Next is we also want to increase the availability of data. Say for example, if you updated your Facebook profile, then you don't want your Facebook profile to be updated take like long time. You want that, okay, if I updated my Facebook profile now, it will be available instantly to all my followers, all of your friends. So in that way you want to increase the data availability. And if say for example, at a time if there are 1 million people all over the world are updating their Facebook profile, then how does the application process so that that particular update is processed and is available on the news feed of all your friends, or all of that particular person's friend who updated their data. So we don't want it to take time, we want it to be effected, like worked immediately available on each of the person friends data. So this is another reason why we need data integration. Third one is to unify your data system. So there are some ways. So consider for example, if there is a way where for any application, say for example, weather prediction application. So weather prediction application, what it does is uh, it has the previously stored like huge big data which is already stored in terms of what was the weather last year, what was the weather like for last 10 years, what was the weather in last 1 or 2 months. Then it has it is capturing some data from like what is the sun, like what is the intensity of sun, how much weather, how much rain, if rain is happening, uh, how much is the moisture, how much is the solar intensity, and like similar kind of data, uh, moisture, rainfall, solar intensity, pressure. uh, so we need to combine this data now. uh, all these data have different format, all these data have different range and all. Now to kind of predict the actual weather, we need to combine these information. Uh, and if you have any application, that application does not have so much kind of processing or storing capability that can like kind of first convert the data into one format, then kind of combine everything to make it available, to make it accessible, and to create this particular application to give the exact weather. Okay, combine all these data and tell the user that okay, the weather today is going to be rainy, uh, and this all happens before actually it rains. So it can tell you that okay, at 10 p.m. or sorry, at 8 p.m. it's going to be rain. So if someone is coming from office at 8 p.m., then they need to carry an umbrella with them, or they can tell that okay, today is going to be, there is a storm coming. So if there is a chance of storm, then people will be, or all those involved people, say for example in terms of whoever is going to go to see the beach, or or those people who are like catching fish, they will be kind of alerted before. Anyway, my aim here is to say that the data captured is in different format, and for the application to execute, we need to kind of convert all the data in one format, uh, so that the application can execute and give the useful insight for all the associated users, or for general human being. Finally, the aim of all these application is to kind of increase the data collaboration. So start collaborating the data, or start again going back to the Uber example. Everyone want to visit or travel from their source to destination. So if there are less number of cars, then we need to consider, uh, or if there is one car who is receiving kind of a request from multiple users via Uber app, then that particular driver need to make some decision that, okay, I want to take that particular person because that person is near my location. So the main aim here is to kind of uh, combine all the data and make some collaboration for the sake of human being. And finally we want to add a value to our big data. So okay, we captured all the data, and using all the data we are giving a value, either is in terms of one particular application such as Uber, or a big application such as uh, weather prediction. So in terms of characteristics, so there are few specific characteristics of big data which are defined in terms of V's. So let's see, these are the, although like depending on the application or depending on the source where you are reading, the characteristics can be defined from 3V to 5V. So here I'm explaining all the 5V's. So the first V is volume. As I already discussed that nowadays we are talking not in terms of like exabyte, not in terms of petabyte, we are talking in terms of exabyte, yottabytes, and in future it will be kind of zettabytes. So uh, we are getting data, like this data is huge, and all these data is created in different from different sources. So the data going scale, so the scaling of data is going at a very fast rate. By 2025, a research shows that we are having 275 million smart devices available all across the world. And say, for example, if we have 275 million devices, and if just one device is creating kind of just 1 GB of data in 1 hour, then you can imagine what will be the volume of data in 20, by 2025 in terms of like exabyte and all. So there I'm considering just 1 GB of data. I already discussed that like Tesla and all, they create like kind of 20 terabyte of data in 1 day. So you can imagine how big the data is going to be in future. Second is the volume. This is the variety. In terms of variety, we can see that data is in like different forms. So Zoom, if you consider Zoom data, then Zoom data is in terms of user login, how many users are logging, uh, what video they are accessing, and how is their network got connected from one user to other user. Usually it is via like you are connected to the Zoom server at US or Silicon Valley, and then that particular server is giving you the location to another user which is in some any other location. We have Amazon. If you consider Amazon spend money, then we have to consider how many users are logging, how much money or which device or which stuff they are purchasing, what time they are purchasing, their invoice and all. Again, if we consider Facebook data, then how many likes each user are getting at any moment of time, like data, their login access data, what time they are accessing, how much time they're spending on the Facebook, what they are uploading, whether they are watching video or whether they are just checking the images. Again, in terms of like, previously we have simple like, now we have different kind of like, we have unlike. When we talk about YouTube, how many people are streaming, which data or which video got more number of hits in terms of, again, like, dislike, which video is watched not only by user, which video is watched in which region, so that it will use some other technology to kind of stream or store that data in in some way, so that user of that particular region can easily access with the minimum time. Similarly, we have data from Twitter, how much tweet a person is doing in at a time. Again, tweet can be just text, like free form text tweet, or tweet is containing some image or some video as well. How many people are retweeting that particular tweet? I'm not going to talk about TikTok at all. Similarly, in terms of Google search, how many people are searching, what keyword or term they are searching. Recently, YouTube launched a very good video on Google, that what was the Google search for last whole year in just 2 minutes. So you can see that, okay, what are the top keywords searched in 2021, and so many others. So all these data are not in the same format. All these data in the different format. So it is a big variety, and if there is any application which kind of combines at least few of these application, it is very challenging. Again, in terms of velocity, data is created at different different speed. We have some of the application are very fast, uh, like a smartwatch or a smartphone. They kind of create a data at smooth, some soft rate. Okay, this is the rate it is creating data. So they already have a defined number of byte which they are going to generate, while there are some sensors which may not create the same amount of data. Say for example, if there is any like a smart sensor in a building, and that particular sensor acts when there is any activity happening in the building. So if there is no activity happening, then the smart sensor is not even monitoring that those sensors are in a sleep state, so there is no data generation. It shows that the data rate can vary. When there is a person, then the data, the amount of data generated by that particular sensor increase, otherwise it's zero. The other system on the backside, the system which is processing the sensor data, has some mechanism that understand, okay, if we are not getting any data from the sensor, it means that there is no activity happening in the building, or something like that. So the velocity is or the amount of streaming is very different for different application and different data source. Talking in terms of veracity, all the data are not very certain. uh, Giving an example of smart traffic, where we have some cameras installed on the street, and if there is an event happening, then that particular camera can capture kind of 20,000 or 50,000 cars passing, because there is a concert happening in the nearby area. So all these cars are passing, and passing the whole day. But otherwise, there is very less number of cars passing. Like, say for example, 50 cars are only passing in one particular day. Giving another example of tweet. Say for example, Republic Day is coming soon. So on the Republic Day, you can see there are the number of tweets with the hashtag Republic Day is will be very high, while other day you don't have that many tweets with the hashtag Republic Day. So if there is any processing happening with just hashtag Republic Day, or with just hashtag India related function, then that particular operation can happen with only that particular day. So if there is any generic tweet kind of handling a functionality, it is a bit complicated for them to understand, okay, just for that particular day we are having this much tweet, and otherwise we don't have that many tweet. So the main aim of discussing this veracity is the data is not very certain, data is very uncertain, and it is very hard to kind of know the uncertainty of data. Not only the simple uncertainty, there is one more thing is, say for example, if there is any fault happen with some sensors, the sensor is fitted on the river bank to know the level of water at any particular period of time, and there is any issue with that particular sensor. So what that sensor perform is, the sensor will send some faulty data. So that faulty data is and it is very hard for the application, or for any system which is kind of evaluating that data, to know which data is faulty data. Or sometimes what happens that if you are receiving data from someone else, then some of the data may not be completely filled. The best example is a survey. So if you are taking part in any survey, then You have like 50 questionnaire, and some of the questionnaire, uh, and you asked someone like 100 people to fill all the 50 questionnaire. Sometimes they don't understand the question, so they don't fill the questionnaire. And in that particular way, that some of the answers are like unanswered, some of the questions are unanswered, and when someone want to process that particular like combined survey, then it is very complicated for them to give a value for those unanswered value. They can do either like they say that, okay, uh, for all the unanswered they can fill for just one option, or they can say that, okay, these are unanswered. But when they kind of overall want to get some value, or get some useful information, then it will become a bit complicated to say that that particular data is correct. So we need to consider this uncertainty or this incompleteness of data in some way. Finally, the main aim of all these, like volume, velocity, variety, and veracity, is to get value from the data. We want to process our data, or we want to uh, get some value for the best of humankind. Next is the challenges. So there are a lot of challenges in terms of storage and processing for the big data. First one is again accessing variety of files. So if you have just simple PDF file, so you can open the PDF file with Adobe format, Adobe app. You can open the PDF file with PDF reader. You can open the PDF file with some other ways as well. Similarly, if I give you an example of image file, so there is one image file, but the image file can be either in terms of like JPEG format. The image can be in the format of GIF format, or in the form of PNG format. Again, similarly, if there is any video, the video can be available either in uh, like WMV format, or MP4, or movie format. uh, we can like these operations, or this variety of file can be for any type of data. So it's very complicated to access a variety of file. So if your application, or if your system has just one kind of like video reader, say for example, if you have just MP4 reader, but if you are getting some data from some other source, in say for example AVI format, then it becomes very complicated for the application, for the MP4 to read that particular AVI format video. Even if it kind of opens, then the encryption, or then the conversion may not be that accurate. Say for example, if there is any associated caption with the video, it may not be like, there is a lag between the caption and the speech, or it may be possible that there is a lag between the video and audio, which makes the user feeling not very good. So user is not happy with the happy if the audio is lagging, or if the subtitle is lagging for their video that they are watching. So it need to be considered that how we are accessing the file for any given application. Similarly, what happens, say for example, initially we have a small data, which is like 128 GB of data. Then we have consider a little bigger device, such as tablet or iPad. We have 512 GB of data. Increase to laptop, we can have up to 1 TB of data, or even 2 TB of data. Getting to little bit bigger machine, you can process, or you can save the data on a like big desktop machine or server. What happens, or what if you have more data? You can have multiple small servers at like different location away from your system, that you can access, and you can allow, or you can able to process your data. So that is one of the option. But again, there, since it is a hardware device, so there are chances of failure in terms of disk failure, network failure, or hardware failure. So probability of failure increases. So if you have if you distribute your data on 4 machines or 5 machines, then any of machine failure can lead to the failure. So increasing the number of machine increases, in one way, increases the probability of failure if you're distributing your data. Store data to cloud data center is another example. But again, cloud has their own demerits in terms of security, in terms of how they are handling the data. So we are, although we are storing the data, but that is not always the best case. Then the requirements. What are the requirements of a big data processing model? So now we need some way to process all the big data, and we need to have some programming model which allows us to process and program our application to perform or to get the desired result. So there are actually four requirements. The first requirement is it need to support some big data operations. So it can kind of split the volume of data. We can access the data at very fast rate. We can distribute the computation to different node. So if we have a bigger application, or if we want to perform some operation, so rather than performing all the operations on just one machine, we can distribute our operations on different machine, or different places in some way, and later on we can kind of combine all the operations and all the results which we received. Next is it need to have some kind of fault tolerance. So if there's any fault happening, it can easily handle the fault tolerant. So first thing is to replicate the data partition. So if there are some data partition, then it replicate, and it can have multiple copy of same data, so that if we want to access, or when we want to access, we can easily access that particular data. Next is it can recover file whenever needed. So although, like, if we lose some data, or if some of the machine can fail, we have to have some way so that we can recover our file, and we can easily recover in short period of time. Third one is it's flexible to add more storage. So if our requirement increases, we can easily uh, able to add more storage, so that it can it can save our data, or it can store our data just at runtime. It is optimized for specific data type. So we don't want a generic, like very generic application which is eligible for table. If we have one application which handles like tabular format of data, that particular application may not be able to, or that particular infrastructure model may not be able to handle the graphical data if our data is in graph format, or if there is any application which just handles the big data, like even if that is able to handle big data, but the data is already stored, that particular application is not able to handle the data which is streaming, or which is the data which is coming in time series manner. So we need to consider, for each particular application or for each particular type of data, our application need to be optimized. Although a first application can perform batch data processing application is able to perform or process for a stream application, but then we are kind of not utilizing our resources in a proper way, or in a smart way. So we need to have the programming model which is optimized for a specific type of data. One of the example is this Hadoop, and this is the picture of Hadoop cluster at Yahoo, which is one of the best example of big data processing model, where we can define our application depending on the type of data. It is fault tolerant. It saves multiple copies of data, and we can add or reduce resources in terms of storage at runtime. If our processing requires more storage or more processing, it can replicate at runtime to reduce the overall time consumption, or to give the result in a far, like as fast time as possible. So say for example, like few years ago, New York Times, they got a question that their goal is to make the entire archive of article available online. Like they have 11 million article available from 1851. The task was to translate 4 TB of TIFF image to PDF file. All those like archives are available in TIFF image, and the task was to convert all those TIFF image into PDF file. The solution they want is they want to use Amazon Elastic Compute Cloud EC2 and simple storage system S3. So the thing is, what they did is how to assign tasks to different workers in efficient way. What happens if tasks fail? How do workers exchange result? And how to synchronize distributed task allocated to different workers. So these are like kind of they get these questions, and then their aim is to solve these questions, because Hadoop is a kind of they have multiple workers, and each worker is like processing or performing independently. So they have to consider some way so that there is no failure happens. They can easily exchange the result, and everything is synchronized in such a way so that they can get the result as soon as possible. So there is a concept called divide and conquer. So before discussing like map reduce or Hadoop, it's better to know about divide and conquer. So in divide and conquer, what happens is, so there is any work or job. So the work or job is divided into multiple small chunk of work. In terms of, say for example, if this is a work which is divided into three separate work, W1, W2, and W3. Now each work is allocated to a separate worker.
Just a quick info, guys. If you want to make a career in cloud and DevOps, then Intellipaat provides an advanced certification in cloud computing and DevOps by ENICT Academy IIT Roorkee, and it is taught by IIT Roorkee professors and industry experts. This course is designed to upskill and land your dream job. Now let's continue with the session.
That particular worker performs the task which is required and creates some result, like in terms of R1, R2, R3. Now finally all those results are combined together to give the result. So initially what we are doing, we are dividing the work into different small component of work which can be easily or independently performed, and later on whatever result we are receiving, independent result, we are kind of merging or combining all those results into one overall result. So the solution is MapReduce. The MapReduce uses that particular architecture, like divide and conquer, and this is the solution they used to solve that the newspaper problem, to convert all the TIFF image into PDF file. So MapReduce is an abstraction to organize parallelizable tasks. What it does is it kind of abstracts and it organizes what are the initially it finds what are or how many parallelizable tasks we can create. It also depends on not only on the task size, but also on how many machines or how many modules are available to process these tasks. So then it applies to algorithm. Algorithm has to adapt it to fit MapReduce main two step. So the first step or first algorithm is just map, which uses a data processing like collecting or grouping or distribute intermediate step. Finally, there is a reduce step, which just collect and then create a digest or create the final result which is required or desired. So map reduce task, one is map and other is reduce. So it is based on a key value pair. So map, what it does is, so we provide like key value, key and value, like data in the format of key and value. With the key value, it kind of like applies them and divide the whole data, like if there is just k and v, key and value, so map, it divides the data in different key value pairs. So there is a key value like key 1 with value 1, key 2 with value 2, and so on, depending on, again, depending on the size of data as well as the size of machine available or number of machine or number of cores available, depending on how we are programming. Then map can be applied in parallel to each of these items. Like for each key, we can apply the mapper operation uh, on the input data set and producing another key value, like which is K2 and V2. Finally, the reduce, what it does is it kind of checks the value for each key. So for each key, how many values are there? And finally, it will kind of give the overall result. Another feature is so for mapping, what happens that a mapping list is a list of data element. So we are providing a list of data element, which is input list. And actually on that particular input list, we are applying a mapping function. So if you see in this figure on top, it is we have an input list, and those independent components can be extracted from that input list. After applying mapping function, we get some output list. So here there is a one-to-one relation. So for each of these function, we are getting one independent result, and this overall operation is known as mapper, or yeah, mapping. This overall operation is known as actual what is mapping operation is happening. It transform each element individually to an output data element. So again, it is one-to-one relation. So if we have one input, it always, the mapper always generate one output, at least one output. Again, coming back to the reducer, so it accepts the input which is given by the mapper function. Here I'm not talking anything about the shuffle function and all. Consider there is no shuffling. So just input list is input list creates output list for mapper, and that particular output list acts as an input list for the reducer. So reducer kind of aggregate all those values together to give us just one output value. Reducer function receives an iterator of the input value, and with each key value, it kind of combines, first matches how many key and how many value, and finally gives the result. Okay, these are the keys and these are the values available for this particular input list. So if we see the overall data flow, what happens is that uh, we got a big data. Like, so the overall architecture is that each node will receive some amount of like processing or some operation to perform. Then we are applying some mapping process, and most of the time it creates like one to one. So for each node it creates one, but not always. Sometimes it happens is that even if we are, say for example, if we have some application such as read count, so we have a data file and we want to read how many words are there, and how many words are repeated for how many times. First is, if we have just one application, that how many words are there, that is very simple. But if we want to see that, okay, how many words are there and how many words, like say for example, the is repeated how many times, then we have a, like, word is a key, and the number of repetition is the value. But if our application is just to count how many words are there, it is very simple. So our key is just word, and our like value is the overall count. So for the second application, which just gives that, okay, uh, how many like words are there and how many count, like what is the overall count of the word in this particular book, it is very easy. So in that particular case, it just doesn't return a lot of repetition. It can return just one output, is that, okay, this is the, like, key is the word and value is how many words are there in that particular file which is received by node 1, and similarly for other. When we go to reducer, so here reducer will receive just one file, saying that, okay, this particular file or this particular piece of the overall file has total number of word as, say for example, 500. Second node has word as key, and the number of like value is 200. Similarly for third one, it is 700. And finally reducer will say that, okay, this 500 is just 500, this is 200. Then we don't need three reducer, we need just one reducer, which kind of accepts 500 from node 1, 200 from node 2, and 700 from node 3, and combine is 7 plus 5 is 12 plus 2 is 14. So overall it is 1400 words are there. But if we want to see that, okay, what is the word and how many times the word got repeated, then the mapping process is different. Then the mapping process, what it does is, it kind of checks what are the unique word and how many time that particular word is repeated. So here the output will be how many unique words are there, key will be how many unique words are there, like what is the unique word, and then value is the number of repetition. Now in this case there are some shuffling required, then, because for example the is in node 1 as well as in node 2 and as well as in node 3. So then we don't want like overall, we don't want that, okay, some d come to node 1 for reducing, some d go to node 3. We want all the key with the name d goes to node 1. So that's why we need some shuffling. So shuffling, what it does is, it kind of just reshuffle based on the key. So all the keys can be brought together to one node, or as less number of node as possible. If it is not able to accommodate on one node, then we can have multiple number of a kind of shuffle phase. First shuffle phase kind of try to combine for one level, and then at second shuffle phase it will try to combine at another level. Finally we can, like, all those words can goes to just one reducer. So again, giving an example, so we have a file, this file is created in input splits. Now this input, we have, these are the map wave, these are mapped, and finally all these maps are kind of, as you can see, as you saw, that all these maps are not moved to same reducer. So there is some shuffling happen that we are not seeing, but finally all the similar kind of tasks are sent to the same kind of reducer or same type of reducer. Similar thing is repeated if we have like more number of file, or if we are like performing some some streaming kind of application. Finally, after the completion, we will get the output, and output will be, if we have word count with unique word, then we will get that, okay, these are the unique word available in this book, and this is the count in this whole book. Giving a closer look. So closer look is, we have mapper or map. So map function will receive the input key value pair from data storage. These input key value pair are kind of distributed in some key and values. So for each mapper kind of processes and then create some keys and values. Now those keys and values are kind of transferred or sent to the intermediate or barrier or shuffle. So that kind of shuffles the key value, and finally all the, so here if you see there are two mapper. Both the mapper has key value 1, key 1, key 2, and key 3. Here, this shuffling, what it does is, all the value or all the result with key 1 is brought to this reducer. So now this reducer has like key 1 value is 10, so key 1 10. Here key 1 20, so key 1 20. Now this reducer combines, okay, both have key 1 and the value is 20, 10 and 20. So it will combine, and the result output is key 1 and 30. So this is very basic example. We can use this to process or to perform different kind of tasks as well. Example is just word count. Say for example, we have a word. So map takes an input file which is a.text, b.text, and c.text, and it outputs as emit one word one. Reducer kind of add together all value to same word and emit word and total count pair. So see the example. So this is a file. A.text is the quick brown fox. B.text has the text, the fox ate the mouse, and C say that how now a brown cow. Now when we have mapper, we wrote the mapper function will kind of emit. So this is the kind of pseudo code for the mapper, which kind of say that, okay, file name and what is the content of file. For each word in the file, it just emit. So these an independent word. What is the number? So number is 1. Quick is another word, so quick, and number is 1. Again, brown now 1 and fox 1. Similarly, the process is repeated here. Finally, in reducer, it is getting different kind of output, and initially it starts with sum is like overall sum is 0. For each value in values, I think it will be better if we see the the result. So this is the input. We are passing this a.text to mapper 1. We are passing the b.text to mapper 2, and we are passing the c.text to mapper 3. Now this is the reducer. After this mapper performs, it captures this d1 brown 1 fox 1, d1 fox 1, d again one more 1. So there are 2d. It has some more like 8 and mouse. It also, this other one has how now, so how 1, now 1, brown 1, and cow 1. So now in the shuffling phase, what happens, these operations or these words are shuffled. So this the brown and fox is brought to reducer 1. From mapper 2, the fox and the are brought to again reducer 1. For mapper 3, this how now and brown are brought to reducer 1, and remaining are brought to reducer t. So reducer 1 will result that brown has 2 copy, or 2 instance, 2 repetition. Fox has also 2 repetition. How has 1, now has 1, and D has 3. Similarly, reducer 2 will give the result that 8, cow, mouse, and quick all has just 1 repetition. So in this way, we can see that how uh, the word count application is using this map reduce to get the result or to get the word count with the number of repetition, how much they are repeated. Example URL. So this is another example. So in this example, we got some data which has the value in terms of date, time, user ID, and URL. Like what time someone is accessing the data, what time someone is accessing the URL, what is the date, what is the user ID, and what is URL. Actually, this is a realistic application from one of the supermarket, such as like Reliance Mart, where they want to know that how many people are buying, or how many people are kind of accessing that particular website at any given instance of time, or in one particular day, or say for example, if there is any survey happening which want to know that this particular URL is visited by how many user, and at what time, so that they can kind of increase or decrease the resources. So these are the kind of Java code which can be easily kind of implemented and run in the machine. This is map, again URL. So we are just finding what URL, like if the input is URL1, so this is URL1. Again, another user is also accessing, like user ID3 is also accessing URL1. So it shows that URL1 is accessed by 2 people and URL2 is accessed only by 1 people. So this is very generic or very simple kind of application. So MapReduce is a programming model, which is kind of what we studied till now, is very abstract. Abstract way. Okay, we need to kind of perform divide and then conquer, perform divide, do the processing, and then combine the result to get the abstraction. So the programming model is abstraction. Now we need some kind of framework which actually perform or does this, which has some runtime library and is written in some programming language. So although MapReduce can be supported to like support large data volume, provide fault tolerance, enable scale out, but we need some kind of infrastructure, or we need some kind of way that can actually implement this MapReduce. So there are many implementation of MapReduce available, but we here in this lecture we are going to discuss only one, which is Hadoop. So Hadoop ecosystem is great for big data. It has like kind of 4 Ws and a H. So we will define the architecture or ecosystem of Hadoop in like 4 Ws and H. What is in the ecosystem? Why it is beneficial? Where it is used? Who uses it? And how do these tools work? So these are the five like 4 Ws and one H for the discuss. So now we will see Hadoop, which is a kind of infrastructure application for big data or for MapReduce. But it is not only for MapReduce; it also provides another features as well. So the question comes is, what does Hadoop offer? So Hadoop offers, first is it enables scalability. So it provides a parallel computation framework that allow we can process our computation or any operations in a parallel way. We can easily distribute our application, and each of the parallel node can perform independently regardless of how and what other nodes are processing. It can easily handle the fault tolerance. I will discuss a little bit later about the redundancy. So there are like different type of redundancy available in Hadoop that easily captures the fault tolerance. There are different type of nodes available in terms of name node, data node, which holds the data for different kind of processing operations, and we have different copy of data as well. It optimized for a variety of data. So it is specific for specific type of data. So if we specify the data type, we can design our own application for only that particular data type, and it will be specific for that particular data type. It facilitates a shared environment in terms of automatic parallelization and distribution. So in terms of shared environment, we can, like if we have a big server or big machine, we can distribute the server in terms of parallel. So some of the nodes are executing this like Hadoop or MapReduce for one application, while some other nodes may not be participating for the Hadoop. They may be performing some other operations such as big data, another type of big data operation, or just generic operation, or even staying idle. It also provide value. So it is well supported by the community. The Hadoop community is very strong. So if you have any question, you can ask in the community through the Slack channel or through the GitHub commit request. They will help. They are always ready to help. Again, IU scheduling. It also allows us like input output in terms of how we are scheduling our Hadoop task. In addition to all these things, it also allow to monitor each of the nodes and overall the machine. We can easily get the status update. There are different type of benchmarks available to kind of test our Hadoop infrastructure, what we have created or what someone is going to create before actually even deploying their own application. The basic architecture of Hadoop is given here. So we have the lowest layer is Hdfs, which is Hadoop distributed file system. Next one is Yarn layer, which is yet another resource negotiator. On top of Yarn, we have so many things. Like one side we have MapReduce, on other side we have either Giraffe or Storm, Spark or Splink. Directly on Hdfs, this HBase is also running. On parallel of Hdfs and everything else, we have either Cassandra or MongoDB. And finally, on the left hand side, we have Zookeeper, which helps in monitoring the overall system. If we see the basic or the like main or essential components of Hadoop, is then we have Hdfs, then we have Yarn, and we have MapReduce. All the remaining applications may or may not be available in any at any instance of time. But if we are saying Hadoop, we are always saying that it must contain an Hdfs system, it must contain a Yarn, and it must contain a MapReduce. So the first component that we are going to discuss is Yarn. Yarn shares Hadoop across different applications. So if we have different kind of applications, say for example, MapReduce uses batch kind of application where we have a big stored data or archived data, and we want to process on Hadoop. It will also like help us to use some time series data or a time series data using like Storm or Flink. Spark is also used for a kind of MapReduce batch data usually, and Giraffe as well. So this Yarn is not only for MapReduce, but it can also support some other kind of application. So what is Yarn? So Yarn, first is it acts as a connecting link between high level application, which is if you see in this figure, which is kind of Hive or MapReduce and Spark, and the lower level, which is lower level Hadoop implementation, which is the file system. It converts Hadoop from just simple MapReduce to a overall big data processing core, which not only allows Hadoop but also allows some other kind of big data applications such as a Storm, Spark, and a Giraffe. Uh, uh, Previously in the Hadoop implementation, there was no Yarn. It was added in the Hadoop version 2.0. So if you see Hadoop ecosystem, so in the previous Hadoop ecosystem, we have just Hdfs, and on top of Hdfs, we have MapReduce. So the mappers and reducer are directly interlinked with the file system. On top of MapReduce, we have Hive or Pig, depending on the type of application. But in Hadoop 2.0 implementation, we added like they added a layer of Yarn because uh, actually adding a layer of Yarn makes this MapReduce a bit more flexible, not relying directly on the HDFS system, also allowing different type of applications to use the file system provided by Hadoop. So in terms of Hadoop 1.0, it allows only MapReduce task. No other applications uh, such as Zookeeper or Storm Spark are supported. Also, the file system, because the linking between the nodes of the mapper and reducer and the file like HDFS are very strict. So the resource utilization was very poor. So to reduce the resource wastage, increase the resource utilization, along with the allow different type of application to use the HDFS file system. This Yarn was added. So it not only allows, as I already discussed, it not only allows MapReduce, but it also allow like Spark and Storm, uh, increases the resource utilization by allowing different type of application to execute. And even for one data set, we can execute many application depending on the type of application that we are executing. So it provides a core services with the help of two long running daemon. So Yarn has two long running daemon. One is resource manager. Resource manager is like each of the cluster has their own resource manager. uh, uh, Depending on the type of cluster, it traces the resources in the cluster to check whether the resource availability is there or not, which kind of applications are running on that particular resources, and how frequently we need kind of context switching for the resources. The next component or core services is the node manager, and node manager is available on a per node basis. Here node represents kind of like virtual machine or containers. It monitor each node and container, and then like notify the resource manager, okay, these nodes are available, and then resource manager makes a decision to execute the mapper and reducer task on the nodes and the or the containers available. So node manager is kind of more linked towards the lower level uh, of this Hadoop architecture, which kind of interact more with the Hdfs file system, while resource manager interacts a little bit more with the upper layer, such as Hadoop, or such as like other applications such as Spark or Storm. Depending on the number of mapper required, or depending on the user defined how many mapper is desired for any application, resource manager requests or uh, asks the node manager to kind of sometimes even create the number of nodes, and then a resource manager allow to execute those mapper and reducer task on the nodes. It is like there is no one-to-one relation between a node and a mapper reducer task. Sometimes it happens that even on one node we can run multiple number of mapper or reducer, or even there is some possibility that if we explicitly specify that one node is able to run just one mapper task, then that particular node does not run more than one task. Next one is this HDFS or Hadoop distributed file system. So in Hadoop distributed file system, it is a kind of file system which is used by Hadoop. So it has this is the basic architecture of HDFS file system. So here we have kind of there are two main components. One is name node and other is the data node. Say for example, there is a client read some data, and those data the client request the name request the name node that, okay, just tell me where's the data. See for example, client want to know where the data is stored. So initially client wrote their data or provided their data to the HDFS architecture, and HDFS architecture stores those data file or data component on different data nodes. Now when the user want, or when the client or user want to read their data, the client requests for name node that, okay, where is my data. They provide some basic metadata information, and name node then like kind of already have a stored metadata in terms of what is the name of data node, or what is the rack where that particular data is stored, how many replicas are there, what is the exact file location on the system. And then it kind of let the data node know that, okay, this client want to read this particular data, and it also returns some values to the client, that particular file, so that client can directly read that particular data from the given data node. So name node and data nodes are kind of very linked. Name node is kind of the master, and those data nodes are slaves, depending on the application requirement for each client request. Say for example, if you have some data, those data are stored at the data node. So data node is the exact place or exact position where the data is stored. Name node is kind of just a reference or a master which allows, or which has the information about where the data is stored. So name node store the name of the node or rack. What are the replicas? Because we need to replicate the data at different places to allow the fault tolerance. So how many replicas are there? How many, like, where are those replicas? What are the files, or what are the data nodes in terms of file system location? And also some other metadata information in terms of what are the freshness of the data. I will talk a little bit later about the freshness of the data or data node. So if or when client submit a data to the HDFS file system, name node just receive the data, and if the data is already divided in block, it can store the data on different machines rather than just on the one machine. So the data got kind of distributed on different machine. Name node just saves the metadata, and data nodes actually saves the data. So the data is saved on the data node. Later on, when the client either want to read, or when we are going to perform some map reduce or some Spark or Storm application execution, so that particular request which I discussed like just previously, like this node manager requests the name node that, okay, we need this particular data, or like using the in terms of metadata. Then name node asks the data node that, okay, or name node gives the location of the data node to the node manager, and then node manager directly retrieves the data from those data nodes. So this is the data with 5 different files. This file is distributed, and it got repeated. So in Hadoop, we always kind of replicate the data. So at least 3 replicas are created in Hadoop, but user can explicitly specify more number of replica. And depending on how important is the application, more number of replicas can be created. So in this example, it shows that this is a normal kind of a file which has 5 separate component. This 5 component is divided, and randomly, like depending on this Hdfs like distribution algorithm, it is divided and stored on these 5 machines. And this name node stores the metadata information, and like in terms of replicas as well as the file location of each of these files or each of these documents, and which can be like either returned to user or node manager or map reduce depending on the application requirement. In HDFS, file is split into 128 MB blocks. So if you are storing your file in MapReduce, sorry, in HDFS system, the file is always split into small chunks of 128 MB blocks. Although at current time, Hadoop allows us to reduce or increase the number of increase or decrease the number of sorry size of block, especially if your data is not in terms of 128. They allow you to create different type of or different size of the split. But if you're not specifying anything, it will split the data, it will split the whole file or data into 128 MB blocks. So all the data except the last one is in terms of 128 MB. Block is replicated across several data node, and usually 3. So again, if you are not specifying how many replicas are created, it usually create 3 replicas for each block. So each block has at least 3 replica in the HDFS system. There is a single name node store. So name node stores kind of the metadata which contains the file name, block location, and some other metadata information. Usually there is only single name node, but uh, there may be more than one name node, which is kind of secondary name node. It is optimized for large files in terms of sequential reads, and the other thing is files are append only. So there is no way the files can be kind of added or read. uh, you can't rewrite the file, you just can append only file, but you can delete the file as well. In terms of name node keeps a directory tree of all the files in the file system and tracks where across the cluster the file data is kept. So if there is a file data, it kind of has a cluster storing all the information about the file system. It does not store the data, as I already told you that name node doesn't store any data actually. It just store the metadata of the data. All the data are actually stored in the data node. A client application talk to the name node whenever they wish to locate a file, or when they want to add or copy or move or delete a file. So client cannot talk to data node. Client can only talk to the name node. So if you see the figure, so first is the client provide a file name to the name node. Name node kind of checks their own data, their own structure, where they have this structure of what is the name of the file, if the file name is valid or not. Second, if the file name is valid, is that particular file name is available in their cluster? If the cluster, if that is available, then what is the block ID, and what is the data node name? Uh, and if everything is found, then it can return the block ID and a data node to the client, and client then directly read the data from the data node. But initialization is always happen with the file name. Name node is also copied in the form of a secondary name node, and for each name node, because if there is just one name node, and if that particular node where this name node is running, or if that particular virtual machine where this name node is running, if that fails, or if there is any issue happened with that particular name node, all the access to the data node is just vanished or lost. So to avoid that particular scenario, name node is also copied. Sometimes, like we call it secondary name node. We can create at least 2 or 3 secondary name node, uh, which are kind of updated regularly depending on how we set it. At least one secondary name node is always available with the Hadoop distributed file system. But again, we can create our own name node, depending on our requirement, or depending on our application access. It also adds a kind of name, adding a secondary name node adds a checkpointing, which kind of checks. So at regular interval, Hadoop distribution like Hdfs checks whether the secondary name node is valid or not. uh, so sometime what happens that mm, if the secondary name node is not updated for a long duration of time, then whatever is stored in the secondary name node may got lost. So to avoid any loss of secondary name node, it is better to have this uh, to have a regular checkup of the secondary name node to see whether it is updated with the recent value or not. If it does not feel, or if it does not uh, found the secondary name node to be updated, then it instantly create another secondary name node and kind of remove the reference of secondary name node, previously stored secondary name node, so that the new secondary name node has the recent information about the name node. And as we know, name node stores the information about the data node. So data node stores the data in HDFS file system. A functional HDFS file system has more than one data node with data replicated across them. So the data is kind of distributed. Again, there are more than at least 3 copies of data is available. Data node respond to the request from the name node for file system. Since name node and data node follow a master slave architecture, so whenever data node requests or uh, asks for access, like either in terms of read or write to a data node has to respond to all those access, allowing to read or to kind of update or write. A client application can talk directly to the data node once the name node has provided the location. But actually, that particular access is very restricted. So client cannot read any block or any name node data. It can read only that particular name node data which is allowed, or which it got request, which it get as a result from its request to the name node. Similarly, MapReduce operations assigned to task tracker instance need a data node. So the thing is, if there is a MapReduce task performing, so that particular mapper task, if that particular mapper task request or needs some data, it can also directly receives from the data node if that particular data node, if that particular data or that particular node is allowed to be accessed by the name node. Instance can be deployed on the same server that host data node. So there is one good thing with the data node and those mapper and reducer tasks is that Hadoop always try to uh, reduce the number of node that it can run. Um, since the execution of any task on using mapper or reducer requires the data, and the data is stored in the data node. So it may be possible that the mappers are running on some other virtual machine, and data is located in some other virtual machine. Uh, so to get or to receive the data from mapper to the data node, it requires some kind of there is a network issue. So to reduce the network latency and to kind of increase or fasten the process of the data transfer, they always try to run the mapper on like same or very nearby node where the data is already stored, which is data node, depending on the application. Not only that, after this data got processed by the mapper, sometimes some of the result data got stored again on the data node, which can later be read by the reducer file. So in that particular way, a reducer will also try to or need to run as nearby as possible to the data node. However, since reducer or the number of reducer are much less as the number of mappers, so it's better to run the mapper task on the on or nearby nodes as the data node, to reduce the network traffic and to improve the overall execution. So like inside name node, this is a snapshot of a file system. We have a file system with the like file 1 has a replication factor of 3, file 2 has a replication factor of 1, and file 3 has a replication factor of just 1. Here in terms of block ID, it is storing like block 1, 2, 3. File 2 is storing block 4, 5, 6, and file 3 is storing 7, 8. So if you see in this figure, uh, data node is so these are the data node. On first one, uh, 1, 2, 5, 7, 4, 3. So since file 1 has a replication factor of 3, so you can find there will be 3 kind of replicas of 1. So 1 is on all 3 data node. 2 is also replicated. 2 and 3 are also replicated. So you can find 2, 3, 2 and 3, and 2 and 3 are also here. In terms of 4, 5, 6, they are replicated only twice. So 4 is here, but 4 is not available here, while 4 is available on third data node. While in terms of 7 and 8, they are just they are not replicated. So there is just one copy. So 7 is on data node 1, while 8 is on data node 2. So in terms of Hadoop, when we define the when we don't specify any replication factor, then Hadoop automatically tries to replicate for 3, replicate with the factor of 3. So there is a 3 copy always created, but we can increase or decrease the replication factor. Mostly, if the application is big and it requires less number of copies, then we create more number of replicas. But if the application or overall application has more number of components, then we kind of reduce the number of replica to save the resources. Because if we are creating more number of replicas, then we have to store each replica on a different server or different node, and that costs the user. So usually if we don't define, Hadoop automatically creates 3 replicas. But if we define, then Hadoop will kind of follows our instruction when we are writing our own MapReduce application. If you have 3 data node and you already define your name node like this, then these values are stored directly on the data node and is available for either the client or user or the mapper or reducer function to read or to update. Inside name node, we have this file system and edit log, periodically update with the housekeeping and backup of name node and metadata. So this is very good thing is that in terms of name node, and these are the data node available. So all these data nodes send a heartbeat signal at a defined time interval. So at each time interval, these data nodes are a kind of uh, telling name node that okay, we are alive, or we are active storing the data. And if the name node doesn't receive this heartbeat signal from the data node, it kind of assumes that the data node may not be available now, or even if the data node is available, they are corrupted, or they are not processing if it doesn't receive the data node. If it doesn't receive the heartbeat from the data node, and after not receiving the heartbeat after given period of time, it kind of recreate another node with the copied file, because the name node already have the replicated replicated data node. It removes the that particular location from the file system, like image or file system uh, address, and saves the removes the previous information and update the newly created file system information, and it also update the secondary name node information. So this heartbeat signal is very important for between the communication between the communication between name node and data node. The other good thing with Hadoop is it automates where the file is located, so we don't have to kind of save the file. We don't have to specify, okay, save the file on machine 1 or on machine 2 or on machine 3. It automatically locates and saves the file. How to handle failure? It can handle as with the help of this heartbeat signal. It handles the failure and data loss. If there is any data loss, if there is any chance of data loss, it kind of replicates and create more number of replicas. If there is any name node failure, it restart another node with the same data, and then and in that way it can kind of stop or make the system bit robust. How to divide the computation? Again, we don't have to think about how to divide the computation. There are rules already specified, as I said, that this Hdfs divide the data with 128 byte chunks. Also, this MapReduce of Hadoop, they kind of divide how much data need to be processed just on one node. So that uses how much data can be processed, or how we can divide the computation among different machine. User or programmer doesn't have to worry about that. Also, in terms of scaling, if we have like kind of more data in future, then it automatically create more number of data node for saving, and also it create more number of mappers and reducer for kind of scaling or performing more number of operations. So increasing the number of operation, user doesn't have to worry. This MapReduce and this HDFS file system along with yarn will manage and handle the scalability issue as well. We are going to see little bit about Amazon Elastic MapReduce. So we all know about AWS. So AWS provide the MapReduce in terms of Elastic MapReduce. It provides a web-based interface and command line to run Hadoop jobs on EC2, where data you can store on S3. So this Elastic MapReduce uses the feature of Amazon EC2 plus Amazon S3 to perform this MapReduce operation. Here you can monitor jobs and shut down machine after use. Small charges, it charges little bit small for performing this monitoring and this MapReduce on top of EC2 pricing. So if you want to have more control over your Hadoop, where your Hadoop runs, you can launch a Hadoop cluster on EC2 manually with your script. So you can also write a script. I will first show something little bit about this on the browser. So this is the Amazon EMR, Elastic MapReduce. Here, it kind of easily run and scale Apache Spark, Hive, Presto, and other big data workload. So we can run our MapReduce easily on this Amazon EMR. All these information are already available here in terms of how to create this Amazon EMR, and then few case studies are also provided. They also give some customers. So if you are interested, you can go and have a look at this. Although it is not very complicated, I will show you. I have some screenshot of execution on Amazon EMR. It's not that complicated. If you are familiar with working on Amazon, like Amazon EC2, you can easily work on this. So when you are working on this Amazon ECR, you can create a new job flow here. You can define by selecting new job flow, create a new, You can specify your new job flow. You can specify the type as streaming. Streaming job allow it to just single step mapper and reducer function in language other than Java. Uh, I didn't discuss much about the overall implementation of MapReduce. So MapReduce is implemented in terms of Java. So the basic or the best way to work with the MapReduce is if you are working or if you're writing your own application in Java. But MapReduce also allow this streaming process or a streaming application where you can write your own program in any different language, and you can kind of interact with MapReduce using this streaming feature. At that time when this kind of screenshot was taken, that time it uses streaming. So I know streaming, and I'm sure currently also, like when last time I used MapReduce, I used a streaming application because I was working on Python program. So I was writing Python program, and I was trying to interact with the I was trying to perform some operation, some optimization operation with the help of MapReduce. When you specify that, then they want to ask you the location where your data is. So I was this application was running a simple word count and specify the path where your data is stored. Then you have to specify where the output location will go. So output location is where you want to save your data. So here it's saved in the bucket, like S3 bucket. Then you have to specify what is the where is the mapper and reducer function. Since you already saw that it is using streaming, so we can specify our mapper in Python program. So it specifies that, okay, Python program is here. So this is the example provided by the EMR. So you can use that. And reducer is just simply aggregate. And you want to create how many instance you want to create. So it asks you, and you can say that, okay, I want 4 instance maximum. What are the type of instance you can specify? So it automatically create the instance, and now you can see your job is running. After running, like after short period of time, you can see the result in your own file, like own bucket which you specified for in the step 3, and then you can get your own result. So the thing is, when we are running MapReduce, we also need to consider sometimes in terms of performance, whether our application is performing right or not. So to verify or to check the performance of our MapReduce infrastructure, there are many benchmarks available. I specify few of the benchmark here, just mentioning few of the benchmarks. In terms of design quantitative benchmark, we have this like test sort or measure. It measures kind of Hadoop's fault tolerance, how fault tolerant is that. It measures the Hive's schema flexibility, whether it is flexible or not. The basic one is this NN benchmark, which is also name node benchmark. We have an MR benchmark, which is MapReduce benchmark. These two are one of the most popular benchmark to evaluate the performance. In these benchmark, you don't have to kind of create your or write your own mapper or reducer function. You just run these benchmark with the specific your MapReduce function or your MapReduce infrastructure. And then these benchmark will kind of evaluate and let you know that, okay, how efficient is your MapReduce infrastructure, or how efficient is your Hadoop infrastructure. To evaluate, you can compare it with RDB, like relational database, and some other data programming model. These are some of the other features of the JobSCAD, where you can use MapReduce. Like current state of affair is currently people use like FIFO for job scheduling. But in terms of research, there are so many ways where you can use use MapReduce for job scheduling. Like in terms of research, there are some cycle scavenging scheduler available that uses MapReduce function. Also, there are some MPI workload available that can also use MapReduce. But these are like kind of future research projects.
Just a quick info, guys. If you want to make a career in cloud and DevOps, then Intellipaat provides an advanced certification in cloud computing and DevOps by ENICT Academy IIT Roorkee, and it is taught by IIT Roorkee professors and industry experts. This course is designed to upskill and land your dream job.